The moon. It would be an unusual situation where there would be an individual who has not seen the moon in at least one of its phases, for instance, full, that we can see here. There are very few people who can say they've seen both the near side of the moon and the far side. When we see the moon, we are typically seeing the near side. But some few people have been able to experience the far side in spaceships that have gone around the moon. You can see actually a significant difference between the two sides. The dark and light pattern of the near side versus the incredible density of cratering on the far. This pattern that we see on the near side has led people to name much of what they saw, and you can see that there's a consistency in the naming of all the dark areas. Mare, 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 Mare. These dark areas were thought to have been water, and thus they got the name a sea. Our first lunar landing of the Apollo 11 with humans on it landed in the Sea of Tranquility. A famous crater, one of the largest, that's easy to see in the full moon phase for sure, is the Tycho crater. This dark area, the moon's mare, comprises about 16% of the moon's surface. And the mare are so named because early astronomers, as I said, thought they were seeing water. Kepler gives these areas this name. The Maria, plural of mare, are at a lower elevation than the rest of the moon, and they are filled with basalt, which is an extrusive volcanic rock. That means it comes out onto the surface, extrudes, and it was released from the still molten interior of the Earth at the early history of the Earth after impacts by asteroids. And because basalt is so iron-rich, it absorbs a lot of sunlight as opposed to reflecting it, and that makes those areas darker than the lighter areas, which are part of our moon vocabulary. So we should know this word mare, this plural Maria. Eventually you're going to need to know this word basalt when we study rocks, because it's a common rock on the surface of the Earth. We already know that actually from studying ocean crust and continental crust. But the rest of the surface that we see, this lighter color, is known as the highlands, the second vocabulary that is important. The lighter areas of the moon, again, made up of heavily cratered anorthosite rock, a different type of igneous rock. And this from a beautiful photograph taken in 2008 from Denmark. And again, the mare and the highlands with the famous Tycho crater. Continuing with moon vocabulary, we have the moon's albedo. How much light does the moon reflect? How much light does any celestial object reflect? The reflectance, the amount of reflectance of the sun's light is known as object's albedo. The Earth has an albedo, the moon has an albedo. And it turns out that the moon's albedo is not particularly high. It's at about 30%. I think we scale albedo from 0 to 1, essentially, so say 0.3. And or 0.03. To our eye, it appears to reflect a lot, but that's because it's just close to us. The Earth also has an albedo, which is higher actually than the moon's because of the combination of our clouds, wakes in the ocean, and we have an abundance of reflective ice, which is melting, thus actually lowering albedo, our albedo. Another vocabulary, part of the vocabulary of the moon is the impact crater. And from Wiki, I say that an impact crater, or Wiki says, an impact crater is an approximately circular depression in the surface of a planet, moon, or other solid body in our solar system or somewhere else. We've never seen anything close enough outside of our solar system to really talk about. Formed by the hypervelocity impact, means extremely fast impact of something smaller than the object it's hitting. Doesn't mean it's a small object, it just means it's smaller than the object it's hitting. This is in contrast to a volcanic crater, such as if you've ever been to Oregon, you know there's a place called Crater Lake, which is a volcanic crater. and that's from the result of an explosion or internal collapse of, say, the dome of a volcano, whereas impact is driving into an otherwise flat surface, raising a rim on the outer edge and a floor that is now lower in elevation than the rest of the land around it. And if it's a big enough impact crater, can often have a little mountain in the middle, which is part of the physics of impacts. And again, this is from Wiki. Here's something from another website which shows impact craters on the far side of the moon. And to quote the website, this photograph looks obliquely across the central part of the moon's far side. This region is virtually saturated with craters. This type of intensely cratered surface is typical of most of the moon's far side and of those parts of the near side that have not been or were not flooded by those lava flows that became the Maria. The average age of this region is probably 4 billion years old, whereas the Maria are younger. Ejecta is the material that's flying out as a consequence of an impact. So the lighter material here is ejecta from the impact. And then sometimes the impact is so large that it creates this beautiful pattern called a ray or a crater ray. And that would be these beautiful lines emanating from the impact site. And here again we see the anorthosite of the highlands versus the basalt of a mare. A rill is a meandering line found all over the moon. You see these in many images of the moon, these meandering lines. It's not known exactly what causes them, but could be that the remnants of lava that was once flowing on the surface or below the surface. Sometimes, and we see this on the surface of the Earth, we have these things called lava tubes that can form under the ground, and lava is flowing under the ground, and then the tube collapses, and then part of the surface falls in. So you can see that might be the case with this rill. And then you can likewise see how many hundreds of small impacts were striking the moon. The last bit of vocabulary I think that we want to look at is called regolith. And this from a NASA website. The lunar surface is covered by a layer of unconsolidated debris. Unconsolidated means not completely stuck together, called the lunar regolith. It would be, we have a regolith on Earth. We often think of it as soil. The thickness of the regolith varies from about 5 meters on mare surfaces to about 10 meters on highland surfaces. And again, that doesn't mean you sink into it. It means that you have to dig through it to get to the solid rock beneath. And we want to take a quick look at a image that, or a little video of a lunar rover crossing the regolith. So let's do this. And here we see this lunar rover raising the regolith, raising this dust. The regolith is the dust that is being raised, and it's extremely fine. Let's take another look at it. The dust is extreme. Where's my cursor? Cursor, come in. Oh, did it again. Okay. Astronauts reported that, and we know from having brought it back, that it's extremely fine material. In fact, the first man who walked on the moon, Neil Armstrong, one of the first things he did was, after he stepped down, just in case something had gone terribly wrong, right as he stepped out of the lunar orbiter, which you can see in the picture at the beginning of this little shot. I'll go back to it now. The first thing he did was take a sample of the lunar regolith. There's the lunar orbiter, which would blast off with the astronauts and take them back to the command module that was going around the moon. So they took a sample immediately of the regolith so that they would make sure if there was an emergency, they could get back to Earth with something. So if you ever watch, there's some good Apollo 11 video that's now out. So I'm going to quit Chrome. Actually, I'm going to go back here. Hopefully this is working. So the far side of the moon was only seen completely in 1959 when a Soviet satellite took photos. So that scared Americans, and we decided we needed to get to the moon first. And by 1968, we'd sent up a human-filled capsule, 3 astronauts, Apollo 8, who went around the moon, didn't land, and came back. It's not well understood why the two sides are so different, with so many lava fields, Maria, on the near side, and so many impact craters on the far. But one thing you can think about is that with that far side always away from the Earth, that objects coming in could more easily hit that far side, than objects having to pass by the Earth and hitting the near side. So probably a lot of objects that might have hit the near side of the Earth hit the Earth instead of the moon. And then we're going to eventually need to answer this question: why did it take so long for humans to see the far side of the moon? Let's take a quick look at some recent analysis, or new, I shouldn't say analysis, but the Chinese have gone to the far side. They were the first ones just 2 years ago.
China is aiming to send a lunar probe to boldly go where no probe has gone before.
And they have done it.
The Chang'e 4 is heading to the far side of the moon. That's the half that always faces away from Earth. Previous probes and rovers have landed on these parts of the moon. If all goes according to plan, the Chang'e 4 will land here, the massive 2,500-kilometer Von Karman crater, near the moon's south pole. China wants the Chang'e 4 to study the composition of the lunar surface, to learn how the far side compares with what is known about the near side. Remote observations indicate that the moon's far side has a much thicker, older crust and is pockmarked by more numerous and deeper craters. The Chang'e 4 is also designed to set up a container of seeds and silkworm larvae to see if those organisms can grow there. But it might not all be smooth sailing. China could face a huge challenge keeping in touch with the moon, because the moon itself will block most radio communications. Scientists will have to rely on a satellite launched in May 2018 to relay signals between the Earth and the probe. China's lunar ambitions started 30 years after the United States and former Soviet Union ended their moon programs. If the Chang'e 4 succeeds in its mission, it could help open a new chapter with clues about the mysterious origins of the moon and the universe itself.
All right. I'm not going to necessarily comment on whether it will usher in a new era on the universe itself, but it may. The interesting thing that they did talk about there is this notion that because the moon, say if this, my hand is the moon here, or this ball of string is the moon here, and the sun is shining on the far side, I'm looking at the moon from the Earth, I'm the Earth, right? To get information back from the far side, you need to have a satellite that's off at a right angle, or maybe not quite a right angle, to the side of the moon, so that you can send information to the satellite and then back to my face, the Earth. And that's a technological problem of going to the far side of the moon. Where'd the moon come from? The current theory has a Mars-sized planet named Theia colliding with the Earth about 4.5 billion years ago. And Theia slowly accretes to the size of a small planet, just like the Earth is accreting at this period. This is the very beginning of the solar system. The Earth is not solid. This is another mass of material that's banging together. They end up on the same orbit, but they're not at the right distance where they neither would gain nor lose ground on each other. So what happens is that the Earth and Theia slowly get too close, plus the gravity of other objects in the solar system create a uneven orbit for Theia, which then eventually causes it to crash into the Earth. And this is a little computer simulation of what that might look like. Boom. And again, we're at the point where the Earth is not solid. So this is relatively recent, 2019 computer simulation. A lot of people have been doing this for the last 10, 15 years, making simulations. A lot of people disagree with the results. I don't really understand this one completely because this moon ends up going back into the molten Earth. But the bottom line is that something about smaller than us hit us, and the two objects now share similar characteristics, which leads people to believe that it was a collision. Then we'll take a quick look at how the near side of the Earth has changed over time. So the evolution of the near side post collision with Theia. And the Theia collision, again, about 4.5 billion years ago. So this is going to show us the moon after it's already revolving around the Earth. Here we have this, again, magma-filled object, which is slowly cooling in the absolute emptiness of space, near 0 degrees absolute temperature, Kelvin. And then a huge collision, we think, one of the earlier ones, which forms what's called the Aitken Basin near the South Pole. So that's soon after the moon has solidified some kind of external crust. You can see the ejecta, and then heavy bombardment for, it looks like they're thinking 300 million years. And this is going to form on the near side the Maria that we then are familiar with now. Again, the collisions then forced the lava to the surface to flow out onto the original crust. Thus, you get these two different types of surface on the near side, something you don't really see on the far side, or not to this extent. So the basalt-rich versus the anorthosite-rich rock. And then just the constant bombardment for, this is what, 2.8 billion years of bombardment until our neck of the woods became, we had the objects, the Earth and the moon had swept up, vacuumed up debris in our orbital path, and now it's only the occasional asteroid or object that it's been perturbed in its orbit that could hit us. And that's us pretty much now. So it gives you a sense of the scale and timing of these amazing transformations. This is just a quick map of where we landed on the near side with the Apollos and then Soviet ones. So the first lunar landing is here, Apollo 11. Then they sent Apollo 12 over in this region. 13 never made it. 14 was in here, near, not too far from 12. 15, and then 16, and that was our last mission. 16 is here, sorry. So they got to the highlands, finally. They'd spent a lot of time in Mare, and here, right on the edge of the Marian highlands. So wanting to get different types of lunar material back to the Earth. Moon facts that I would like to be able to go over together. I'm going to give you websites where you can find these things. What's the gravity on the moon, its orbital period, its period of rotation, period from one full moon to the next, different. So there's a sidereal month and a synodic month. Its average density, its age, circumference, axial tilt, just like we have one, it has one. Its distance from the Earth. How much velocity do you need to get off the moon? We know how much you need for the Earth. Its apogee and perigee, when is it furthest and closest to the Earth? Average high temperature, the near side, the average low temperature overall. Its eccentricity, how elliptical is its orbit. Its orbital inclination, so that's how it orbits the sun, and the source of moonlight. What are the two motions of the moon? Well, the moon rotates and the moon revolves. It rotates once in the same amount of time that it takes to go around the Earth. And the consequence of that is that we only ever see one side of the moon. The moon revolves around the Earth once every 27.3 days from a stellar reference point back to that same stellar reference point. That's called the sidereal month. We meant that month for the Earth earlier, sidereal referring to a star. So you have fixed star, back to that same fixed star. But with the moon, it's not back to the phase it started with. It takes 2.2 further days to get back to the same position in relation to the sun, and that's the synodic month, 29.5 days. And here's the diagram. Here we're looking off at the moon and a distant star. The distant star could be on this side of the earth, and the moon goes around us. 27.3 days, it's back to that distant star, but it hasn't revolved around to where it can now line up for the new moon phase in relation to the sun. And that's again because in that 29.5 day period, we've gone around the sun about 30 degrees, 1 degree per day. And that angle change in relation to the sun causes this difference between a 360 rotation around to a fixed star versus phase to phase, 27.3 days versus 29.5. The moon also rotates once every 27.32 days, the same rate of rotation as sidereal revolution. And again, the consequence of this, we never see the far side of the moon. It is always facing away from the Earth. You need to go up into outer space to get a good view of it. The moon, as seen from the Earth, changes its appearance over the course of the lunar cycle. So from the standpoint of an observer on Earth, we watch the moon go through its cycle of 29.5 days as what we say, its phases change. These changes, again, are the phases of the moon. There are 8 significant phases that humans have marked out. And the sequence always starts with the new moon and ends with the new moon. How many days does it take for this one lunar cycle? 29.5. The moon is either waxing from the first phase, which we call the new moon, which we cannot see, or waning from the full moon, which we can see very well. So we're either waxing, growing from new to full, or we're waning from full back to noon over this lunar cycle, 29.5 days. The first half takes about 15 days from new to full. The second half takes about 15 days from full back to new. When waxing, the moon is lit on its right side as seen by an observer on the Earth. When waning, the moon is lit on its left side. And I think, actually, I should have said lighted. I don't think lit is correct there. So I apologize for that mistake, and I hope I can fix it in some future version. Lighted on its right side, and when the waning moon, it's lighted on its left side, as seen from Earth. One lunar cycle is 29.5 days from new moon back to the next new moon. One more time, 29.5 days. That's about a month. That's where we get the word month from this cycle that the moon displays, puts on as a show for us. The new moon starts here directly between the sun and the Earth, where, because the moon is lit on the back side, the far side, we don't see the front. Not to mention that it rises with the sun and sets with the sun. So not only is there no sunlight hitting the side facing us, it's also out in the middle of the day. But then the moon moves 13 degrees per day, if you do the math, 360 degrees, right? Plus a little, divided by the 29.5 day cycle. Then our first phase that is named is the waxing crescent, which takes a few days to get to. Then to our first quarter, another few days. Then to our waxing gibbous, waxing, gaining light on the right side, until finally, after about 15 days, we are greeted with a full moon which rises as the sun sets. Then the moon begins to shrink, and it's waning, back to gibbous. It's rising now, late. It rises this sometime in the evening, 9 o'clock, and sets in the morning, rising at midnight, setting in the middle of the day at noon. This third quarter, lit on the left, and the waning crescent rising at 3 in the morning. That's why you don't see the waning moon that often unless you're observant in the early morning. You can often see it then, or you're a night owl. You'll also note here how the moon, from the point of view of someone off the Earth, is always lit half light, half dark, or always lighted, half light, half dark. The phases of the moon as seen from Earth. Now, if we were in school, I would just fill these in with you. The first phase would be the new moon phase, the waxing crescent, the first quarter, the waxing gibbous, the full moon, the waning gibbous, the last quarter, the waning crescent. Let's name them by their sight. Well, we don't see it. That's what this little dark spot's meant to show. That would be a new moon, the first phase of the cycle. 3/4 on the left. Well, that's waning. When it's lit on the left, it's waning. If it's 3/4, it's gibbous. Gibbous meaning sort of a hunched back, sort of like with a hump. You could have called it, I guess, 3/4, but that's not the word that's been used, and it's accepted as part of the cycle. It's waning gibbous. Then, well, it's lit halfway to full. We call that the first quarter of the lunar cycle. The full moon, half of the lunar cycle, unmistakable. Though often people think that they're seeing a full moon for several days. The full moon is full really just for an instant, but still can be beautiful over several nights. Near full, just past full. Lit on the left. If it's lit on the left, it's waning. This is a waning crescent. Lit on the right, the same shape, but lit on the right. Only will be seen in the evening, just after sunset. Waxing crescent. And I should say that this waning crescent is rarely seen by us because it rises at 3 in the morning. And by the time you're waking up, the sun is up and you can't really see it anymore. So you have to get up early to see the waning crescent. Same way that you have to see the waning gibbous rises at 9 in the evening. And by the time it's at the celestial meridian at lunar noon, well, 6 hours have already gone by. So it's about 3 in the morning. So you need to be a night owl to see that waning gibbous through the night. The last quarter, again, it's a late night, early morning moon, lit on the left, last quarter. And the waxing gibbous, often seen by people because it's getting close to full and everyone's getting excited. You can see that because it rises at about 3 in the afternoon, and you can see it through the evening. And it'll set about 3 in the morning. Waxing gibbous. And again, if we were going to look at the moon from outer space, say above the North Pole or South Pole, we would see the moon lit in half dark, half light, all the time. And because it revolves so slowly, it can get quite hot on its lit side and quite cold. In fact, the Chinese, which sent that mission up to the far side of the moon, they would have 14 days in the light, and during some of those days, in the middle of the day, it got so hot they'd have to shut their lunar rover down, and then they would have 14 days in the dark, no solar energy to create electricity to do what they needed to do, so they would put their rover into hibernation. So you have to think about this tremendous range of temperature between the lighted side and the dark side of the moon. Let's now name each phase again from the Earth's perspective, starting with waxing crescent. It takes about 3 to 4 days from the new moon. Each one of this sequence of time is in relation to the new moon. The full moon takes about 15 days from the new moon. The last quarter is going to take you about 22 to 23 days from the new moon. Again, the moon revolving around the Earth. 22 to 23 days later will be in its last quarter phase. The waxing gibbous taking 10 to 11 days, just after a week, in between a week and 2 weeks. The new moon starts the cycle and ends it after 29 and a half days. The waning gibbous after 18 to 19 days, just past the full moon. The waning crescent after 25 to 26 days, we're just about back to start again a new lunar cycle and our first quarter after a week or so. So again, You can see how a month evolves. 1 week, 2 weeks, 3 weeks, 4 weeks. Questions. The different shapes of the moon visible from the Earth are called phases. When the moon is gaining light from the Earth's perspective, waxing. When the moon is losing light from the Earth's perspective, waning. What percent of the moon is always lit by the sun? This would be from the point of view of an observer off the Earth. 25%? 50%? 100%? Depends on the phase. Well, D and A and C are wrong. Half of the moon is always lit, lighted by the sun, and half is in dark. The half that faces the sun, 50%. True or false? The moon shines because it produces its own light. False. Sunlight reflects off the moon, but not evenly, as we now know. What motion causes the moon's phases? Moon's revolution around Earth in a counterclockwise direction. The moon is waning from full to new moon. The moon is waxing from new to full moon. And again, our rising and setting times, our lunar noon, which is the moment the moon crosses the celestial meridian. You should be somewhat aware of these times. You've actually watched the moon in your short lives, and you can now connect the phase to the time of day that you're seeing it. When you see the moon only in the evening, just around sunset, you're seeing a waxing crescent lit on the right. When you see the moon all night, from sunset to sunrise the next day, it's a full moon or near a full moon. When you see the moon only in the early morning, you're seeing the waning moon, last quarter, or waning crescent, or even the waning gibbous setting early in the morning in the western sky. And again, setting in the same portion or along the same portion of the horizon as the sun, western for setting, eastern for a rising moon, but not rising and setting in the same place as the sun. And there's a good reason for that. The phases of the moon are cyclic and predictable. And with that, we are going to pause and join you later with a second moon adventure.